For over a century, Albert Einstein's general relativity has been the undisputed king of gravity. I mean, it's passed every single test we've ever thrown at it, just with flying colors. But what if I told you it's not the only game in town? What if there's another theory out there, a perfect impersonator, that looks, acts, and feels exactly like Einstein's masterpiece? At least, here at home. Okay, let's get into it.
Seriously, just think about that for a second. What if a theory has been hiding in plain sight this whole time? A secret twin to general relativity, so good at its disguise that for all of our history, we would have had no way of telling the difference. And this is where our story really kicks off, with this idea of a perfect disguise. We're talking about a theory that, right here in our own solar system, is the spitting image of general relativity. It aces all the same exams, gets all the same answers right. But once you get out to the cosmic scale, it starts playing by a completely different set of rules. Look, we have really put general relativity through its paces. We've checked how the sun bends starlight. We've measured that weird little wobble in Mercury's orbit. We've timed signals traveling through warped spacetime. And GR passes every single time. But here's the crazy part. So does our mystery theory. In our cosmic backyard, they are completely identical twins. So, you have to wonder, how in the world could we even begin to tell them apart? How do you actually test a theory of gravity? Well, physicists, being the clever people they are, have developed the ultimate test. Think of it like a universal scorecard that any contender for the gravity crown has to fill out.
Now, it has a really complicated-sounding name, the Parameterized Post-Newtonian formalism. Let's just call it PPN way easier. But the idea behind it is actually pretty simple. It's basically a checklist. It's a set of 10 very specific measurements that tell you exactly how a theory of gravity behaves. To be taken seriously, any new theory has to absolutely nail this test.
And out of that whole 10-point checklist, these two right here are the real heavy hitters. You've got gamma, which tells you how much space itself gets bent by a massive object, like the sun. And then there's beta, which measures how gravity fields add up. Is it simple and straightforward, or is there something more complicated going on? For Einstein's general relativity, the answer for both is just so clean, so elegant. It's exactly 1.
So the big question is, how close to 1 does your theory need to be? Well, the bar is set incredibly high. Based on data we got from the Cassini spacecraft, our measurements for gamma are so precise that any wiggle room has to be smaller than this number. That's about 2.3 parts in 100,000. It is a ridiculously small margin for error. So, what is this mystery theory that can actually meet such an insane standard? Well, it's time for the big reveal. The theory is called Dynamic Vacuum Field Theory, or DVFT for short, and its secret ingredient for gravity is something completely different from warped spacetime. DVFT says that what we call empty space isn't empty at all. Nope, it's filled with this dynamic field, kind of like a cosmic fluid that permeates everything. In this picture, gravity isn't the stage of spacetime itself bending, it's more like ripples and changes in the density of this universal fluid. It is a completely radical way of rethinking what gravity even is. And here's where the theory gets its dual personality. In high-gravity places, like our solar system, this vacuum field acts stiff. It's rigid, it's predictable, and it behaves in a way that perfectly, and I mean perfectly, mimics general relativity. But in the low-gravity environments on the outskirts of galaxies, the field becomes flexible, and that allows a totally new, stronger kind of gravity to emerge. Which brings us to the million-dollar question, right? It's a really cool idea, this stiff and flexible vacuum, but can it actually pass that incredibly precise PPN test we were just talking about? Does the disguise really hold up under that kind of scrutiny? And the answer is yes, absolutely perfectly. When you actually run the numbers through the theory, DVFT predicts that in the high-gravity conditions of our solar system, those key parameters, gamma and beta, are exactly 1. They are identical to general relativity. The disguise is mathematically perfect. Okay, so maybe not exactly identical. The theory does predict a tiny, tiny, tiny deviation. For Mercury's orbit, the difference between what DVFT says and what general relativity says is predicted to be about 1 part in 100 trillion. That is a decimal point followed by 13 zeros and then a 1. It is just fantastically, unmeasurably small. This chart really puts it all into perspective. That little sliver on the left, that's the difference the theory predicts. The giant bar on the right, that's how much uncertainty we have in our best measurements. The difference is literally thousands of times smaller than our ability to even detect it.
So for all practical purposes, here in our solar system, the two theories are one and the same.
But remember, that disguise only works here at home. The second we look beyond our solar system, out into the huge, low-gravity expanses of galaxies, the mask comes right off. And this is where DVFT steps out from behind Einstein's shadow and shows us its true face.
And you might be thinking, okay, if they're identical here, who cares? Why does this even matter? Well, it matters because some of the biggest, most profound mysteries in cosmology aren't happening here in our solar system. They're happening out there, across the galaxies. So what we have are two different cosmic rulebooks. Here at home, where gravity is strong and dense, the stiff vacuum makes sure that general relativity's rules are the ones that apply. But out on the galactic frontier, where gravity is super weak, the vacuum becomes flexible, and a whole new rulebook for how gravity works takes over.
And what problem does this new rulebook solve? Well, only one of the biggest puzzles in all of astrophysics, the mystery of why galaxies are spinning so fast. You see, we observe that stars way out on the edges of galaxies are moving so quickly they should just fly right off into deep space. According to general relativity, there just isn't enough stuff we can see, enough gravity, to hold them in orbit. And that brings us to the two big competing solutions. The standard model says, hey, there must be a ton of invisible stuff out there. Let's call it dark matter, and that's providing the extra gravitational glue. But DVFT offers a totally different explanation. It says there is no missing matter. Instead, gravity itself just gets stronger over large distances, all because that cosmic fluid, the vacuum, becomes more flexible. You don't need to add new stuff if you just change the rules of gravity. And this leaves us with this final, really profound question. Are we on a wild goose chase for some mysterious, invisible substance that supposedly makes up 85% of all the matter in the universe? Or have we this whole time just been working with half the story about what gravity truly is? This theory suggests the answer might not be hiding out there in the dark, but in the very fabric of the vacuum itself.